Hello everyone and welcome to the latest installment of the A-Level 9709 Solution Guide series. In this video we will take a closer look at paper 1-2 from the October-November exam period of 2020. So without further ado, let's get straight into it. Exercise 1 states that the coefficient of x cubed in the expansion of 1 plus kx multiplied 1 minus 2x to the power of 5 is 20. We are supposed to find the value of the constant k. Here we are required to work with the binomial theorem, which you're provided with to the right hand side of the screen. To make things easier, I inserted a part of Pascal's triangle here. What we will then do is apply it to the expression 1 minus 2x to the power of 5. After applying the formula, we can stop once we reach the expression x to the power of 3, since x to the power of 3 multiplied x already leads us to the expression x to the power of 4, which would be beyond the scope of this exercise. In this step here, we just simplify our previous expression. In step 2, we multiply our factor 1 plus kx. At this stage here, we just need to focus on the summons 4x squared and negative 80x cubed. The reason being that 1 multiplied x cubed will provide us with a coefficient related to x cubed, and kx multiplied 40x squared will do the same, since x multiplied x squared also equals x cubed. Finally, we just equate those two coefficients with 20 and rearrange this equation for k and receive our result for k, which equals 5 over 2. Moving on to exercise 2 of this exam paper, where it's stated that the first, second and third terms of a geometric progression are 2p plus 6, negative 2p and p plus 2 respectively, whereby p is positive. We are supposed to find the sum to infinity of the progression. Our key phrase here is geometric progression, and you are provided with its rules to the right hand side of your screen. So in step 1 we are just applying the information that is stated within the exercise and use this information to determine the value of p. In order to calculate the ratio between two terms, we simply divide any successor from its predecessor. So in this case, term 3 by term 2 and term 2 by term 1 respectively. This will help us in setting up the following equation, and cross multiplication provides us with the equation p plus 2 multiplied 2p plus x equals negative 2p squared. In the following step, we simply expand this factor as well as the expression on the right hand side of the equation. Thereafter, we can rearrange it for 0 and then either immediately solve this quadratic function according to the rules that you can find to the right hand side of the screen, or you can go one step further and factorize 2 from this equation, which would allow for us to employ the PQ formula in order to find p. Applying aforementioned formulas will lead to the results that p can either have the value of negative 1 or positive 6, and we will choose positive 6 since it is mentioned in the exercise that p must contain a positive value. Now that we know the value for p, this allows for us to determine the value of the ratio, which we receive by either substituting 6 for p in either of those fractions. Doing so will get us the value of r, which is negative 2 over 3. Following from here, we will be able to calculate the value of the first term of this geometric series, which is simply done by substituting p for 6, and this will get us that the first term has the value 18. Now that we know the ratio of this geometric sequence as well as the first term, we can finally use the formula to calculate the sum to infinity of this progression, and replacing a for 18 and r for negative 2 over 3 will deliver us the result for the sum to infinity of this progression, which is 10.8. Exercise 3 states that the equation of a curve is y equals 2x squared plus m multiplied 2x plus 1, where m is a constant and the equation of a line is y equals 6x plus 4. We are supposed to show that for all values of m, the line intersects the curve at two distinct points. So what we will firstly establish is an equation to calculate the intersection of the line with the curve, which is simply done by equating the equations for both. From here we will simplify the expression and rearrange it for 0, which leads us to receiving a quadratic function. According to the formula for quadratic functions, which you can find to the right hand side of the screen, we should be able to determine that our coefficients a, b, c are in this case represented by the values of 2, 2m minus 6 and m minus 4. Now for those graphs to intersect at two distinct points as required in the description of the exercise, we need to make sure that the value of the determinant is positive, and in order to determine all of the values m for which this expression is 2, we simply replace the variables b, a and c for the aforementioned values. After having replaced all of the values within this inequality, we will expand this expression with the formula for the difference of squares, which you are provided with to the right hand side of the screen. From there we just simplify this entire inequation and rearrange it for 0, and employing either the formula for solving quadratic functions or the PQ formula respectively, we will receive the result that we are receiving the following expression. And looking at the radicand of this expression here, we can see that we are receiving a result that is negative. And since the square root for negative numbers is not defined within the real numbers, we can come to the conclusion that there is no value of m for which the line and the curve can intersect in two distinct points. Next on to exercise 4, where it is stated that the sum Sn of the first n terms of an arithmetic progression is given by Sn equals n squared plus 4n. Additionally, the kth term in the progression is greater than 200, and we are supposed to find the smallest possible value of k. Our key phrase here is arithmetic progression, and what we first try to establish is the value of the first term a, which equals to the sum for n equals 1. And after substituting 1 for n, we will come to the conclusion that the value for a equals 5. In step 2, we will determine the value of d. And in order to determine d, we just need to subtract the values for two consecutive terms. More exactly, we need to subtract a term from its successor. This can be achieved by firstly finding the sum for n equals 2, which is done through replacing n for 2, by which we are getting the result that S2 equals 12. Now, in order to determine the value of d, we will employ the formula for summing an arithmetic series, which you're provided with to the right hand side of the screen. So in this step here, we simply place the variables n, a and d in the formula for the values. So in the first stage, we will replace the variables n and a within the formula for their respective values 2 and 5, and after simplifying the equation, we will arrive at the conclusion that the common difference between the terms of this arithmetic progression equals 2. Finally, we can now use the formula for summing an arithmetic series, which you can find to the right hand side of the screen, in order to calculate the smallest value for k for which the progression is greater than 200. For that, we will set up a corresponding inequality, whereby we will replace n for k and a for 5. After rearranging this inequality, we arrive at the conclusion that k needs to be larger than 98.5, and since k needs to be a natural number, the smallest possible value for k equals 99. Further on to exercise 5, where we are provided with two functions f and g, and in part A we are supposed to find the value of f of g of 7. To calculate this composition of functions, which workings you can find to the right hand side of your screen, we will replace variable x in function f for the function of g of x. Simplifying this expression will provide us with the result, which is 0. In part B of this exercise, we are supposed to find the values of x for which the inverse function of f of x equals the inverse function of g of x. So firstly, we will establish the inverse function of f and g. This is done in firstly inverting the variables x and y. Keep in mind that f of x can be replaced with y, and the same accounts for g of x as well. Thereafter, we will simply rearrange both equations for y in order to receive their inverse functions, which in the case of f will be 1 over 4x plus 1 over 2, and for g 4 over x minus 1 respectively. In a final step, we simply equate both of the inverse functions of f and g and rearrange it for x. In step 1, we subtract the right hand side of the equation on both sides and rewrite the expression 4 over x for 4x to the power of 1 according to the laws of exponents, which you're provided with to the right hand side of the screen. In an additional step, we will multiply both sides of the equation with x and receive a quadratic function which we can solve with the formulas that you're provided with to the right-hand side of the screen. Followers of this channel know that I prefer working with the PQ formula and applying either the reduced or the full quadratic formula. We will come to the conclusion that the values for x can either be -8 or +2. Continuing with exercise 6, where in part A we are supposed to prove the identity of this expression here. So what we will firstly do is to rewrite both of those factors, and factor 1 will be rewritten in a way that both of their denominators are cosine x, and similarly in the second factor the denominator will also be made common to sine x. The expression tangent x equals according to the trigonometric identities that you're provided with to the right hand side of the screen to the expression sine x over cosine x, and 1 which equals 1 over 1 will just be replaced by the expression sine x over sine x. In the next step we just simplify the fractions within both factors and from there just multiply those in multiplying their numerators and denominators respectively. Employing the rules for the difference of squares, which you are provided with to the right hand side of the screen, we can rewrite the numerator for the expression 1 minus sine squared x. Since there is no way to simplify the numerator with the factor of sine x in the denominator, we will attempt to rewrite this expression for cosine x, and this can be done according to the laws for trigonometric identities according to Pythagoras, which you are supplied with to the right hand sides of your screen. Therefore, this expression can be rewritten for cosine squared x, which can then be simplified, and again according to the laws of trigonometric identities, which you are again supplied with to the right hand side of the screens, come to the conclusion that the left hand side of this identity indeed equals the expression 1 over tangent x. Part B of exercise X requires from us to solve the previous equation for 2 tangent squared x for x within the interval between 0 and 180 degrees. To simplify this equation, we will simply make use of the fact that this expression is identical to the expression 1 over tangent x, from where we can easily solve this equation for tangent x, which is done in firstly multiplying both sides of the equation with tangent x. From there we rearrange it for tangent cubed x in dividing both sides of the equation by the factor 2. And finally, with the help of our pocket calculators, we will be able to calculate the angle of this expression for the first quadrant, which provides us with the solution that x equals 38.4 degrees. Since according to the depiction that you can find to the right hand side of the screen, tangent is only positive for the first and third quadrant of a unit circle, we should arrive to the conclusion that there are no further solutions to be found within the given domain. The reason being that the expression of the cubed root of 1 over 2 is a positive number, and for angles between 90 and 180 degrees we would receive a negative result for tangent x. Next on to exercise 7. Here it is stated that the point 4, 7 lies on the curve y equals f of x, and that it is given that its first derivative equals 6x to the power of -1 over 2 minus 4x to the power of -3 over 2. In point A it says that a point moves along the curve in such a way that the x-coordinate is increasing at a constant rate of 0.12 units per second. We are supposed to find the rate of increase of the y-coordinate when x equals 4. Our key phrase here is rate of increase, which is constant, when x equals 4, meaning that we need to replace x for 4 in the first derivative of the function f of x. Doing so with the help of our pocket calculator will help us to come to the conclusion that the result for the y-coordinate equals 5 over 2. Expanding from there, we need to take into account that the point moves at the speed of 0.12 units per second, meaning that we can simply multiply our previous result of 5 over 2 with 0.12 and come to the conclusion that the rate of increase is 0.3. In part B of this exercise, we are supposed to find the equation of the curve f of x, and this can be achieved in integrating its first derivative. which can be done using the power rules which you are provided with to the right hand side of the screen. Simplifying this expression will provide us with the following term: since 6 multiplied 2 equals 12 and -4 multiplied -2 equals 8. What's left for us is to find out the value for the constant c, and this can be done in exploiting the information that was previously given in the exercise, knowing that one point of this curve can be found at the coordinates 4, 7, meaning that we simply receive x for 4 and equate the function with y equals 7. From here we just rearrange our equation for c and should arrive at the conclusion that the value of the constant c is -21. Therefore, the equation for the function f equals 12x to the power of 1/2 plus 8x to the power of -1/2 minus 21. In exercise 8 of this exam paper, we are provided with the diagram ABC, which is an isosceles triangle with AB being of equal distance as BC, which equal r centimeters. Furthermore, it is stated that the angle BAC has the size of theta radians. The point D lies on AC, and ABD is a sector of a circle with center A. In exercise A, we are supposed to express the area of the shaded region in terms of r and theta. So our plan here will be to calculate the difference between the area of this triangle and this sector of the circle with center A in order to receive the size of the shaded area. So firstly, we will determine the area of the triangle, which can be achieved in employing the formula for right triangles, which you can find to the right hand side of the screen. So this area can be calculated as follows. Since this triangle is isosceles, it's sufficient for us to calculate the area of this triangle here and multiply the result with 2. The height being h and the base AC over 2. Since this angle is already given, as well as the length of the hypotenuse, we can calculate cosine for those two sides in conjunction with this angle, which equates to dividing the length of the adjacent side with the hypotenuse, which delivers us the following expression. And after rearranging this equation for AC over 2, we will be able to replace it for the expression r multiplied cosine theta. Similarly, h can be calculated using sine, since the opposite side divided by the hypotenuse equals sine theta, and rearranging this expression will help us in replacing h with r multiplied sine theta. Since 2 multiplied 1/2 equals 1, the area of the isosceles triangle is represented by the expression r multiplied sine theta multiplied r cosine theta. In step 2, we can employ the formula for calculating an area of a sector, which you can find here. Finally, we subtract the area of the sector from the area of the triangle as planned and arrive at the conclusion that this area can be represented by the expression r sine theta multiplied r cosine theta minus 1/2 r squared theta. In part B of this exercise, it is stated that in the case where r equals 10 and theta equals 0.6, we are supposed to find the perimeter of the shaded region, which is here represented in blue. Since the distance between B and C is already given, being r, we need to calculate the arc length of the circle with center A, and in a second step, the length between C and D. So in the first step, we can simply determine the length of the arc employing the formula that you're provided with to the right-hand side of the screen. And after replacing theta and r with the values that we are provided with, namely 0.6 and 10, we come to the conclusion that the arc length is 6. To find the distance between C and D, we need to subtract r from the length of the distance between A and C. AC can be calculated using this equation that we have used in part A of this exercise and rearrange it for AC. Rearranging this equation for AC will deliver us that it equals 2r multiplied cosine theta. From here we will replace r and theta for their values 10 and 0.6 as given within this exercise, and after putting in those numbers into our pocket calculators, we will conclude that the distance AC equals 16.506 Having arrived there, we are finally able to calculate the distance between D and C, which is done by subtracting r from the length of AC. Since the length of r is 10, after subtracting 10 from AC, we will conclude that the distance DC equals 6.506. In a final stage, we can now determine the length of the perimeter of the shaded region, which equals 6 plus 6.506 plus 10, which after rounding equals 22.5. Moving on to exercise 9, where it is stated that a circle has center at the point B, 5, 1, and that the point A with the coordinates -1 and -2 lies on the circle. In part A of this exercise, we are supposed to find the equation of the circle. Since we are provided with the center of the circle as well as with another point that lies on the circle, we will be able to calculate its radius employing the formula of the standard form of the equation for circles. After inserting the coordinate of points A and B accordingly into the formula, we will be able to conclude that r squared equals 45. It is not really necessary to determine the radius, since we are looking for the equation of the circle, which is arranged for r squared. So now that we know the value for r squared, we just enter the coordinates of the center of the circle into this formula and can conclude that the equation of the circle can be represented by the expression x minus 5 squared plus x minus 1 squared equals 45. For part B of this exercise, it is stated that point C is such that AC is a diameter of the circle. Point D has coordinates 5, 16. Here we are supposed to show that DC is a tangent to the circle. In order to be able to visualize the entire situation, I have provided you with a sketch of the problem over here. In order to receive the coordinates for point C, we need to subtract the directional vector BA from point vector B, since we need to travel the distance BA into its opposite direction in order to arrive at point C. For this, we need to insert the coordinates accordingly and conclude that the coordinates for point C are 11, 4. From here we will calculate the directional vector CD, meaning that we will subtract the point vector of C from that of D, and conclude that this can be represented by -6, 12. Finally, to verify whether vector CD is perpendicular to vector AC, we will be employing the rule for orthogonality between vectors, which you're provided with to the right hand side of the screen. After employing this formula accordingly, with -6 multiplied 12 being -72 and 12 multiplied 6 being 72, we can conclude that the dot product between both vectors equals 0. Hence, CD is a tangent to the circle. Moving on to part C of this exercise, where it's stated that the other tangent from D to the circle touches the circle at point E. We are supposed to determine the coordinates of point E. This can be achieved by firstly establishing the equation for the line that goes through points D and C, and a simple way to represent this would be the employment of a vector equation of that line. The coordinates for point D can be obtained in part B of this exercise, and the directional vector CD as well. Now we will transform this equation from its vector form into its Cartesian form. This is achieved by setting up a system of equations, keeping in mind that capital X is nothing but a representation of xy. Thus we can set up the system of equations of x equaling 5 minus 6r and y equaling 16 plus 12r. Now we will rearrange the first part of the system of equations for r and then substitute the expression x over 6 minus 5 over 6 for r in the second equation. Rearranging this equation lets us conclude that the Cartesian equation for this very same line can be expressed by y equals 2x plus 6. Since this line touches this circle, both of the functions have point E in common, which means that in order to determine the x value of point E, we will substitute y in the equation for the circle for the expression 2x plus 6. Then this expression will be simplified employing the rules for the difference and sum of squares, which you're provided with to the right hand side of your screen. From here we will simplify and rearrange this quadratic function for 0, and then either use the extended or reduced formula for solving quadratic equations, which you can find to the right hand side of the screen, in order to find the value for x. Using either of those formulas will let you conclude that the x value of E is -1. Using that result, we can now calculate the value for y of point E in substituting x for -1 in the Cartesian equation of the line above. Doing so will let us conclude that the coordinates of point E are -1, 4. Next on to exercise 10, where we are provided with a diagram that shows part of the curve y equals 2 over 3 minus 2x squared minus x and its minimum point M, which lies on the x-axis. We are supposed to find the expressions for the first and second derivative of the function as well as its integration. So firstly, in order to determine the first two derivatives of the function, we will rewrite the fractional part of the function using the laws of exponents which you are provided with to the right hand side of your screen. The derivative of this part of the function can now be determined with the combination of the power rule and the chain rule, since our argument x occurs within the brackets. So we also need to differentiate the expression of -2x, which equals -2, and the derivative of -x equals -1. From there we just simplify our expression, after which we get 8 multiplied in brackets 3 minus 2x to the power of -3 minus 1. From here we will get the second derivative of our function in differentiating the first derivative. Similarly to calculating the first derivative of the function f, we will again have to employ a combination of both the power and the chain rule, which you again can find to the right hand side of your screen. After simplifying, we can conclude that the second derivative of f can be expressed by 48 multiplied 3 -2x to the power of -4. In a final step, we will integrate our function f, again employing the form that we have previously used to determine the first two derivatives of this function. Firstly, we will rewrite this integration employing both the factor rule, the constant rule, as well as the difference rule for integrations, which you are supplied with to the right hand side of your screen. The difference in this case being the term within the brackets minus x, and the factor within the first part being 2. Now for both integrations we can simply employ the power rule, which you again can find to the right hand sides of your screen. After inserting all of our values accordingly and simplifying everything for as much as possible, which in this case just imply multiplying 2 with -1 over 2, which equates to -1, and dividing -1 with -1 equals 1, which means that all of those factors just disappear, and what remains is this expression at the end. Part B of this exercise now requires from us to find the x-coordinate of M by calculation, and our key phrase is here that M represents the minimum point of the function f. Additionally, we know that this point is located on the x-axis, which means that its y-coordinate must be 0. So since the minimum point is a stationary point, we will just equate the first derivative of function f with 0. In order to be able to rearrange this equation for x, you will firstly have to isolate the expression 3 minus 2x to the power of -3, which can be achieved in firstly adding 1 to both sides of the equation, after which we will divide both sides with the factor of 3 minus 2x to the power of -3, and doing so employing the power rule for exponents, which you can find on the right hand side of your screens, means that we will have to change the sign of the exponent from -3 to +3. Now we can employ the cubed root on both sides of the equation, and from here rearranging everything for x is pretty straightforward, and we should be able to conclude that the x-coordinate of M has the value 1 over 2. In the final part of exercise 10, part C, we have to find the area of the shaded region bounded by the curve and the coordinate axes. So firstly we will have to determine the x values of the boundaries, which are 0 due to the y-axis and 1 over 2 since the curve as well as the x-axis converge in M. So from here we can simply integrate this expression within the boundaries of 0 and 1 over 2, and after inserting all of those values accordingly, we will be able to conclude that the area under the curve is 1 over 24. We have arrived at the final exercise of this exam paper, exercise 11, and here it states that a curve has equation y equals 3 cosine 2x plus 2 for x within the interval 0 and pi inclusive. In part A we are supposed to state the greatest and least values of y. This can be done pretty easily looking at the coefficients a, b, c and d for trigonometric functions, which you can find to the right hand side of your screen, and we should be able to realize that the greatest and least values of y are determined by the shift of the cosine function along the y-axis as well as its amplitude. So to get the greatest value for y, we just add up the y shift with the amplitude, meaning 2 plus 3 equals 5, and subtracting the amplitude from the y shift, 2 minus 3 equaling -1. In part B, we are supposed to sketch the graph y equals 3 cosine 2x plus 2 within the aforementioned interval. And again, with the graph that you're provided with to the right hand side of the screen, we should again know that the highest value for y must be 5, the lowest for y -1, and since the coefficient of b equals 2, our interval can be calculated by simplifying the expression 2 pi over 2, which equals pi. So the lowest point must be right between 0 and pi, which means pi minus 0 over 2 equals pi over 2. The dashed blue line simply represents the shift of the function along the y-axis. In part C of exercise 11, we should consider the straight line y equals kx, where k is a constant and we are supposed to state the number of solutions of the equation 3 cosine 2x plus 2 equals kx within the aforementioned interval in each of the following cases. So firstly, the line y equals kx must have its y-intercept in the origin, since the standard form for straight lines is represented by the equation y equals mx plus b, m being replaced by k and no value for b provided, which means that it must be 0. Thus we can conclude that the straight line intersects the origin. So for k -3, k representing the gradient of the line, which I've put into the sketch of exercise B, we can conclude that there would be no solutions, since the line neither intersects nor touches the function within the interval of 0 and pi. For k equals 1, which line is represented in orange, we can see that we would get 2 solutions, as it would intersect the function at 2 distinct points. And finally, for this line having the gradient +3, which is represented by the purple line, we can easily see that there would only be one solution, as the line would intersect the curve at exactly 1 point. In part D of exercise 11, it is stated that functions f, g and h are defined for x being element of the real numbers. We are here required to fully describe a sequence of transformations that maps the graph of y equals f of x onto y equals g of x. And according to the rules for graph transformations, which are provided with to the right hand side of the screen, we should be able to realize that this expression relates to a horizontal shrink by factor 1/2 and +4, meaning that this entire function would be shifted up along the y-axis by 4. In part E, similarly according to the same rules, we will be able to fully describe the sequence of transformations that maps the graph of y equals f of x onto y equals h of x. So in this case, the expression 2 multiplied f indicates that the graph would be vertically stretched by factor 2 and shifted to the left by -pi/2 according to this expression inside of the brackets, since in order to get 0 as a result for the expression x plus 1/2 pi, we would have to subtract it by the same value of pi/2, which is the same as 1/2 pi. I've been your host Marco from PlanetMaths. Should you derive any value from my videos, please consider to leave a like, comment and subscribe. Thank you for watching. Cheers.